Most of what we know about Earth's deep interior comes from an instrument that never touches rock at all, an earthquake. Every time the planet shakes, it sends waves through the crust, the mantle, and even the core, turning Earth into a temporary, ringing bell. And those vibrations are our only direct conversation with the world beneath our feet. When an earthquake happens, it releases energy in the form of seismic waves. These are not sound waves in air. They are mechanical deformations traveling through solid and molten rock. There are two main types that matter for exploring the deep Earth. Primary waves, or P waves, compress and stretch the material in the direction they travel, much like a slinky being pushed and pulled. Secondary waves, or S waves, shear the material side to side, like shaking a rope. P waves can move through solids, liquids, and gases. S waves can only travel through solids. That single fact, S waves dying in liquids, is one of the main reasons we know there is a liquid outer core at all. As these waves move through Earth, they change speed and direction depending on what they pass through. Dense, rigid rock lets them move faster. Hotter or partially molten rock slows them down. Where there is a sharp change in composition or state, like from solid rock to liquid iron, the waves refract, meaning they bend, just as light bends when it passes from air into water. Some waves even reflect, bouncing back toward the surface. By placing seismometers all over the globe and recording exactly when different kinds of waves arrive, seismologists can invert this data to reconstruct the interior, essentially solving a gigantic three-dimensional puzzle where each earthquake adds a few more pieces. One of the most striking clues is that S waves generated by large earthquakes never appear in a broad shadow zone on the opposite side of the planet. They simply vanish. That absence is exactly what you would expect if something liquid, wrapped around the solid inner core, absorbs them. P waves, which can travel through both solids and liquids, do reach that side of the Earth, but they arrive later and are bent into their own shadow zones by the drastic change in material at about 2,900 kilometers depth, the boundary between the solid mantle and the liquid outer core. From countless such events, we've built what's called a seismic velocity model of the planet, a detailed map of how fast and in what ways waves travel at different depths. This map is our most important image of the deep Earth. So what would you actually experience if you somehow descended through these layers? Let's start near the surface and fall inward. The crust, the skin of our planet, is surprisingly thin. Under the oceans, it can be just about 7 kilometers thick. Under continents, 30 to 50 kilometers on average, with a few mountain routes going deeper. If you could stand at the base of the continental crust, at around 35 kilometers down, the pressure around you would already be about 1 gigapascal. That is 10,000 times the atmospheric pressure at sea level, the equivalent of having roughly 10,000 kilograms pressing on every square centimeter of your body. The temperature would likely be in the ballpark of 700 to 1,000 degrees Celsius, depending on the local geothermal gradient. The rate at which temperature rises with depth, often somewhere between 20 and 40 degrees per kilometer in the upper crust. If you kept going into the upper mantle from about 35 to a few hundred kilometers deep, the chemistry does not change dramatically, but the behavior of the rock does. The mantle is mostly made of silicate minerals rich in magnesium and iron, like olivine or pyroxene. Near the top, it's quite rigid and brittle. This is the part that, together with the crust, forms the lithosphere, the tectonic plates. But by around 100 to 200 kilometers down, temperature and pressure combine to make the rock behave like an extremely viscous solid. Think of something with the rigidity of hard glass on short timescales, but the ability to flow very slowly on geological timescales, like cold asphalt creeping on a hot day. Convection in this part of the mantle, though painfully slow by human standards, centimeters per year, is what drives plate tectonics. By the time you reach roughly 660 kilometers depth, you hit a major transition zone. Under these pressures, the crystal structures of mantle minerals rearrange themselves into denser forms. Olivine, for example, transforms into different high-pressure phases like wadzleite and ringwoodite, and then breaks down into even denser minerals. This doesn't change the overall composition much. It's still mostly silicate rock, but each structural shift produces seismic discontinuities, layers where wave speeds abruptly change. These transitions are so clear in seismic data that we can trace them globally, revealing that Earth's mantle is not just a simple slab of rock, but a stratified, phase-changing engine. Continue down to about 2,900 kilometers depth, and you hit the core mantle boundary, one of the most extreme interfaces on Earth. Here, pressure has reached around 135 gigapascals, about 1.3 million times atmospheric pressure, and the temperature is estimated at roughly 3,500 to 4,000 degrees Celsius, hotter than the surface of many red dwarf stars. On the mantle side, you have superheated, high-pressure silicate rock. On the core side, you have liquid iron alloy, mixed with lighter elements like sulfur, oxygen, or silicon. This boundary is not smooth. Seismic studies show patchy regions called ultra-low velocity zones where wave speeds drop dramatically, possibly because of slightly molten or compositionally distinct rock, perhaps pools of dense, iron-rich material that have sunk from above or risen from the core below. If you were somehow at this boundary, it would not be a flat line. It would be a rugged, thermally and chemically chaotic landscape. Below this lies the outer core, a roughly 2,200-kilometer thick shell of liquid metal. It is mostly iron with some nickel and lighter elements. Here, the pressure keeps climbing to over 300 gigapascals, and the temperature may reach up to 5,000 to 6,000 degrees Celsius near the inner core boundary. Despite this, the iron is not a plasma. It is a dense, electrically conducting liquid, with a density around 10 to 12 grams per cubic centimeter, about 10 times that of water. Convection currents in this molten metal, combined with the Coriolis effect from Earth's rotation, act like a self-sustaining dynamo, generating our planet's magnetic field. It is a planetary-scale version of an electrical generator. Moving conductive fluid cuts through magnetic field lines, inducing electric currents, which then reinforce the magnetic field in a feedback loop. Deeper still, at about 5,150 kilometers down, we reach the inner core boundary, where the liquid iron of the outer core suddenly solidifies into a dense, crystalline sphere. The inner core is about 1,220 kilometers in radius, roughly 3/4 the size of the Moon. Here, pressures approach 360 gigapascals, about 3.6 million times atmospheric pressure, and temperatures are estimated around 5,000 to 6,000 degrees Celsius, similar to the surface of the Sun. Yet, because of the enormous pressure, iron crystallizes into a solid, likely in a hexagonal, close-packed structure. Seismic waves reveal that this inner core is not uniform. Waves travel faster along Earth's rotational axis than along the equator, suggesting that the iron crystals are aligned, giving the core anisotropic properties. There is even evidence that the very center of the inner core, the inner core, may have a different structure or composition again.